Now we're ready to talk about searching through the plan space by enumerating the left-deep plans. Notice that the left-deep plans differ in only three ways. They differ in the order of the relations. Looking at the leaves of the trees on the right-hand side here, we can see that the order of the letters is different, but the shape of the tree will always be the same. So they differ in only the order of the relations. And then in the access method we choose for each leaf operator. Could be an index scan on some index, or it could be a heap scan. And they differ potentially in the join method for each join operator. We'd like to avoid exhaustively enumerating all of these possible left-deep plans. And a key observation here is that many trees share common subtrees, or many plans share common subplans. So maybe we can save work by remembering decisions on our subplans. So this brings us to one of the big ideas in computer science and in control theory as well, which is the idea of the principle of optimality, which was introduced by a guy named Richard Bellman back in the 1940s. And so I'm going to explain it here, slightly adapted to our setting of left deep query plans. And the basic idea is that the best overall plan to an optimization problem is composed of best decisions on the subplans. Another way to say that is the optimal result has optimal substructure. So specifically in our case, the best left deep plan to join tables A, B, and C is either the best plan for joining AB, joined to C, or the best plan for joining AC, joined to B, or the best plan for joining BC to A. All right, because this principle of optimality says that however we're going to build up the left-hand side of the tree, it's going to be a best plan for some subset of size 2. This is great. It gives us two advantages. First, when we're optimizing one of these subplans, like we're trying to pick the best plan for A join B, we don't have to think about how it will be used later on, e.g. when dealing with C. Okay. Similarly, when we're trying to put together a three-way plan, and so something like A join B join C, we can reuse the best results we already computed for the subroutines, namely A join B, A join C, and B join C. And we don't have to think about them again. We can treat them as sort of encapsulated inside a triangle. Okay, so the principle of optimality leads to Bellman's dynamic programming technique, and we'll look at it in the way that it interacts with Pat Selinger's system R algorithm. So we're going to build these query trees bottom up. In pass 1, we're going to find the best plans of height 1. These are base table accesses, like scans. And we're going to record the best plan for each table in a lookup table. Okay, that lookup table will sit in memory. In pass 2, we'll find the best plans of height 2, which are joins of two base tables. And we'll do that by combining the best plans of height 1. Right? That's the principle of optimality. And whatever we get for the best plans of height 2, we'll record them in our lookup table. In general, on pass I, we're going to find the best plans of height I by combining plans from our lookup table of height I minus 1 with plans of height 1 from our lookup table, and record the results back in the lookup table. And finally, our last pass here is going to be a pass n, where we had n tables in our query to begin with. It finds the best overall join order by combining plans of height n minus 1 from our lookup table with plans of height 1 from our lookup table. Okay, so what is in this lookup table? Well, so far it's pretty simple. The key to this lookup table is the first column. It's the set of tables that were joined together. And then the dependent columns here, the other two columns, the best plan is kept for each subset of tables, and the cost of that best plan is kept. So in this example, we have the pair R and S. The best way to join those we found was the hash join of R and S, and the cost was 1,000. The best way to join R and T was a merge join of R and T with cost 700, etc. So this is an example of the data structure we'd want to keep in memory for dynamic programming. So there's a wrinkle when it comes to dynamic programming, and that wrinkle has to do with ordering and physical properties. Physical properties can actually break the principle of optimality in a certain sense, and we need to account for that and fix it again. Let me give you an example. Consider a plan for A join B that is suboptimal. Right? We'll call it P, little p. And this plan is not the fastest plan for A join B, but it has an interesting physical property. It's ordered by X. And suppose that the join with C is on column X. Well, then that suboptimal plan is kind of neat, because we can join A join B with C using sort merge join, and we won't have to sort the left-hand side because this suboptimal plan P is already sorted. So the best plan for A join B, the optimal plan for A join B, may not be sorted by X and requires us to do a sort. Using suboptimal plan P, we don't have to sort the left-hand side of this sort merge join, and the savings might be enough to make up for the difference between the suboptimal plan P and the optimal plan for A join B. Okay, and so we're going to need to do something to expand our definition of the optimal substructure here in dynamic programming, so that we keep this plan A join B that is ordered on column X. We keep that plan in our dynamic programming table. So this structure is going to have to somehow include not only the set of tables, but the physical properties of ordering as well. Unfortunately, not all orders are interesting, and so we can actually prune this a little bit further. So before we give the final answer here, let's talk about what makes an order interesting. The interestingness that we're going to talk about is the physical property of order. When should we care that a subresult is ordered? When is it interesting? Well, an intermediate result in our dynamic programming table is going to have an interesting order if it's sorted in a way that we can use later on in the query downstream. So if it's sorted by an order by attribute, or by a group by attribute, or, as we saw in the previous slide, by a join attribute of a yet to be added join, then we might want to save this apparently suboptimal plan because its order is interesting. And so what we're going to do is we're going to expand our dynamic programming table to now have two columns in its key. It's the subset of tables in the from clause that we're keeping in that row, and the set of interesting order columns. And for each pair of those subset of tables, interesting order columns, we'll keep a best plan. So we'll keep a best plan essentially for every subtree with a different physical property. Okay, so we have AB with none. The best plan for that's a hash join, and it costs 1,000. And then we'll have AB ordered by some columns, let's say A.x and B.y in this example. And for that, we'll keep the sort merge plan, which in this case is more expensive. It's 1,500, but it has this interesting property that it's ordered by A.x, B.y. So finally, the big picture of enumerating all the plans using the Selinger technique is first you figure out the join and scans. You figure out the join ordering, and that deals with the select project join piece of the query. We do this using dynamic programming. One final wrinkle on dynamic programming is that we want to avoid Cartesian products, and we'll do this as follows. When you're matching an I-1 way subplan with another table, so we're in the middle of our recursion in dynamic programming, we're only going to pair up that subplan with that table if either A, there's a join condition between the subplan and the table we're joining it with, or B, all the predicates in the where clause of our query have already been accounted for and so-called used up in the subplan. So we've already used up all the where clause, it's totally satisfied, but there's still tables in the from clause. Those tables have to be joined in by Cartesian product. They don't have any where clause predicates to connect them to the rest of the plan. So that's the only place we use Cartesian products, and that will, by definition then, be at the top of the plan. So we've postponed or avoided the Cartesian products as much as possible. Once we have our join tree of selects, projects, and joins, then we can handle the order bys, the group bys, the aggregates, and all that stuff as a post-processing step. And remember, we have the whole dynamic programming table still with the interesting orders. So we can decide, for example, if an order by over an interesting order is cheaper than a sort over a not interesting order to achieve that order by. Okay? So that's kind of the big picture of how the Selinger optimizer's search strategy works. It's dynamic programming to build the access methods and the joins, and then we sort of paste the order by, group by on top, taking into account interesting orders. Despite the pruning, the left deep heuristic, the avoid Cartesian products heuristic, and the algorithmic benefits of dynamic programming, despite all that pruning, the system R algorithm is still exponential in the number of tables. So we've gone down from a very big exponential problem to a somewhat smaller exponential problem. And it's made it practical for, up to about 15 tables in a join. Beyond that, even the Selinger optimizer runs out of memory in its dynamic programming table, and you have to fall back on a heuristic search strategy. We won't cover that in this class, but there are a number of them in the literature, and new research is going on to find better heuristics still today, taking account of Bellman's ideas of dynamic programming with machine learning, actually, to do clever things.